Tel Aviv University. And
okay. Good morning. Thank you very much for the invitation. It's a pleasure to give here a few lectures here in Jerusalem. The topic of these lectures will be counting independent sets in hypergraphs. And this might sound sort of a bit abstract. So first, let me give some motivation for why we study this problem. So the motivation will be characterizing discrete structures that satisfy certain constraints, and in particular, structures that satisfy certain sort of local constraints, and this will be clear from the few examples I will give. And the examples that my lecture will focus on, there's two of them. So two examples to keep in mind is the Turan problem, where we are given a fixed graph H, and we study graphs G, where we think that H is a small graph and G is a large graph, such that H is not a subgraph of G. And maybe one good example to keep in mind, we'll try to say something about triangle-free graphs. And then the second problem is the so-called Erdős-Turan problem, and this is the problem of studying a subset of the first n integers which contain no k-term arithmetic progression. So a sequence or subset x, x plus d, x plus k minus 1 over d. Okay, so these are the two problems we'll be dealing with for most of the 4 lectures. And somehow, so these are very classical problems. And maybe the first question you can ask in this setting is, okay, so you know that the complete graph contains every graph H as a subgraph. So now we can ask, how many edges can a graph have if we constrain it not to have a copy of H? So if H is a clique, this is the famous problem of Turan. And these questions are fairly well understood. And here in this course, we're not going to be sort of studying the extremal problem of characterizing the maximum number of edges in an H-free graph, or characterizing the graphs which achieve this maximum, but rather we want to consider the family of all H-free graphs on a fixed vertex set and say something about the typical such graph. And same here for this Erdős-Turan problem. It's known, it was proved by Semeredi, that if we want that every subset of the first n integers which doesn't contain arithmetic progression of a fixed length has only less than delta n elements for any positive constant delta if n is large enough. But here we're not going to be considering this problem, but rather the problem, okay, what does a typical set which doesn't contain a k-term arithmetic progression look like? And it turns out that it's fairly helpful to consider these problems in the following general framework, where we have a V, some finite set, and we have a collection H of subsets of the set V, and these are our forbidden configurations. Now, so let's look at. So now we're interested in studying a subset I of V such that no H in H is contained in I. Okay, maybe this sounds a bit general, so I'll try to convince you that these problems are of this particular type. So in problem 1, we let V to be the set of edges in the complete graph on n vertices. And these forbidden subsets H are just edge sets of copies of H in the complete graph Kn. And now any subset I here of V is just an edge set, a set of edges in the complete graph on n vertices, so it's a subgraph of the complete graph. And it doesn't contain any H. It means that if I take any, say, 3 edges that form a triangle, then these 3 edges are not all contained in my subgraph I, which means that my subgraph I is triangle free. Now, the second example, I take V to be the set of the first n integers, and H is just the collection of all sets of the form x plus d, x plus k minus 1 over d, where x, d are integers, and this, of course, needs to fit inside n. And now again, if I look at any subset I of V, so any subset of the first n natural numbers, which doesn't contain any of these sets, it means it doesn't contain any k-term arithmetic progression. So in combinatorics, we often call such families of subsets hypergraphs, and subsets of the vertex set of the hypergraph, subsets I, which don't contain any of the hyperedges or edges of the hypergraph, are just independent sets. So H is a hypergraph, and each such I is an independent set. Of H. So one might say that a large part of extremal combinatorics is studying independent sets in certain families of hypergraphs. Right? Maybe this is, of course, the hypergraphs that we study are somehow very closely related to the particular problem, and it's difficult to try to attack these problems in such generality. But it turns out that for certain counting statements, looking at such problems in this general framework can be very, very beneficial. Now, what are the problems that one usually studies for such hypergraphs? So what are the questions that we ask? First of all, what is the largest independent set in a given hypergraph? So this is, for example, the statement of Turan's theorem. What is alpha of H? We call it the independence number of H, which is the maximum size of I, where I is independent. Now, second question, what are the sets I that are independent and have precisely the maximum number of elements? So here, for example, the theorem of Mantel says that if we look at H, which is the collection of all triangles in the complete graph Kn, then alpha of H will be n squared over 4, and the sets I, which contain n squared over 4 elements and are triangle free, the graphs which have n squared over 4 edges and are triangle free, are precisely the complete bipartite graphs. But the questions that we're going to be interested in are of a somewhat different nature. So we don't want to characterize the maximum independent sets, but we'd rather like to count all of them. So what is the number of independent sets? And the fourth question, which is essentially also a counting question, is what does a typical independent set look like? So what do I mean by this? I will look at the family of all independent sets, then I will choose one uniformly at random, and I'll try to say something about its structure. So the content of this lecture series are methods of answering 3 and 4 for a large family of H. And in particular, we will relate answers to questions 3 and 4 to answers to questions 1 and 2. It turns out that for a large natural class of hypergraphs, somehow these two problems, these two extremal problems, and these two counting problems are very, very closely related. There's some, say, intimate relationship between them, and we'll be developing methods that allow us to take advantage of this relationship and derive interesting counting statements from the existing extremal statements. So today, I'm going to give a gentle introduction to these methods, and today we'll focus on the case where this hypergraph H is too uniform, meaning that each of these forbidden constraints contains only 2 elements. So this might sound like a bit not very rich theory, because somehow all the interesting examples that we know, if we look at graphs which have 2 edges, they're not very interesting, or 2-element arithmetic progressions. I mean, each 2 numbers form a 2-element arithmetic progressions. But it turns out that still, just by analyzing this question for graphs, can give interesting results. And this is much, much easier to understand. So before moving on to general hypergraphs, I'll handle this case. So the goal for today let I of G be the family of all independent sets in a graph G, and the goal for today is to count elements of I of G for, let's say for now, interesting graphs G. Okay. I should mention that if at any point any of you has any questions, feel free to stop me. Now, can we say anything about this question for an arbitrary graph G? So let's indeed fix a graph G and maybe denote by little I of G the number of independent sets in G. Can you give me any bounds on I of G? So what about a lower bound?
0.
Okay, I guess we can do a little better. We can do 1 because the empty set is independent. But if I look at the maximum size independent set, then each of its subsets is also independent. So this already gives me a bound of the form 2 to the independence number. On the other hand, I know that every independent set has at most alpha G elements. So the upper bound will be just the number of sets of up to alpha G elements, which is the sum of these binomial coefficients from 0 to alpha of g. So maybe a good starting point would be asking, how sharp is this estimate? Yeah, so it's close, but it's also far. On the other hand, I mean, somehow in a perfect setting, we would like to determine this number asymptotically up to a factor of 1 plus little of 1, and not only in the exponent, but actually in the base. So if you want to count them asymptotically, then these two bounds are very, very far apart. Even if we're interested in counting them so within a 1 plus little 1 factor of the exponent, so giving an asymptotics for the logarithm of this number, this is still pretty bad. So how sharp? The only case where these two bounds are very, very close is if alpha of g is very, very close to the number of vertices. So if this graph is almost empty, then of course almost every set is independent. So this is good. But it turns out that actually for many interesting graphs that we study, the lower bound is much closer to the truth. And today I'm going to give sufficient conditions for a graph for which I of g is not much larger than the lower bound. So let's say for many interesting g, the lower bound in star is sharp, and today we develop tools to prove it. For the random graph, well, for the random graph, I mean, it certainly should be sharp if you allow for 1 plus log of 1 term in the exponent. But asymptotic probably not. Okay, so maybe let's first think about, there's a very, very easy and natural example for which this is not sharp. If we let G to be just a perfect matching of n over 2 edges, then the independence number of G is, well, it's n over 2 because we can pick only one vertex from each of the edges of the matching, but the number of independent sets in G, an independent set is just, so if we intersect it with every edge of the matching, it's an independent set there, and this is equivalent. So given an edge, we have three possibilities to form an independent set. They're either the empty set, the left vertex, or the right vertex. So here we have 3 to the n choose 2. So the truth is really quite far away from the lower bound, because the lower bound gives us only 2 to the n over 2. And I mean, using very similar arguments, one might convince oneself that if this graph is somehow very, very sparse, then the lower bound cannot be sharp. And maybe taking this a bit further, if this graph contains a set which is significantly larger than the maximum independent set, and this set is sparse, then this graph will contain many more independent sets than just 2 to the alpha of G. Because this matching, I mean, it doesn't have to be the entire graph. We could add something more to it, but the essence is that we have a set which is significantly larger than the maximum independent set, but it's still sparse. And it turns out that if we assume the negation of this, that every set which is slightly larger than the maximum independent set already contains many edges, then this bound becomes more or less sharp. So it turns out that having sparse sets of size greater than alpha of g is the only obstruction to I of g being approximately 2 to the alpha of g. And this statement was proved implicitly in the early 80s in the work of Kleitman and Winston. So this was implicitly proved by Kleitman and Winston, maybe around 82. So Kleitman and Winston were interested in two counting problems, and one of them was a problem of counting a certain types of posets, and the other problem, which was maybe closer to what we do, is the problem of counting the number of graphs without a 4-cycle, number of n-vertex graph without a 4-cycle. This question was asked by Erdős. And while answering this problem, they developed a certain method of enumeration, which leads to the following statement. And today, I'd like to present to you their method and maybe show one application of it to the problem of Cameron and Erdős of counting some free subsets among integers from 1 through n. So this will be the plan for today. So this would be a good time for questions. Yes, I will state. They do not. They somehow implicitly in their proof they prove a certain lemma, which I'm going to present to you now. It's not stated in this form, but I will state it, and somehow it's clear that this is what they actually prove. But in their proof, they already feed some input to this lemma to get a certain corollary. But once you state this lemma separately, then you can derive many similar corollaries by placing this lemma in a different context. But maybe before I state this lemma, because maybe it's not, so it won't be entirely clear what's going on there. First, I'd like to discuss the method of the proof, and then we'll see how to state this lemma. So let's try to follow the history and do it as it was done. So first we present the argument, and then derive the conclusion from it.
So it's also on Dedekind's problem? The same duo worked also on Dedekind's problem?
Yes. Mm-hmm.
So how many independent sets or anti-chains there are?
Yes. So this was the poset problem I mentioned. Mm-hmm.
Yeah.
So the number of anti-chains in posets of height 2.
I think the Kleitman and several other people around this time had various. This also became later, I think, the work with Rothschild and Erdős on triangle free graphs.
No, so the triangle free work on triangle free graphs, I think, precedes this. This is mid-70s maybe. Okay, so let's. I'll call this, or I usually call it the Kleitman-Winston method. This is a certain method of enumerating independent sets in graphs, which was first, to the best of my knowledge, described by them, but later rediscovered by many people, in particular Noga, Alon, and with his work also with Wojta, and also by Alexander Sapojenko. So he had a series of papers using very, very similar ideas. So this method has been around, but when I try to trace it back, this is the first time it appears in print. So the setting will be the following. We have G, which is an arbitrary graph with n vertices. And we estimate the number of independent sets in G. And so before I start writing something, let me maybe explain what is the main idea here. Well, the main idea here is that the family of all independent sets, it looks somewhat complicated. We don't know how to describe it. So enumerating is also, we can say that we want a simple description of this family, which will yield some upper bound on their number. And the idea here is to map these sets into simpler sets which we understand. And then these simple sets we can then count. So in other words, we might say that we plan to devise an algorithm which takes as an input some independent set and then encodes it using a few symbols in a unique way, and then we just count the number of such encodings. Since the encoding was unique and reversible, then we can estimate the number of different inputs. So there will be one definition that will be useful for us, and this is that of a maximum degree ordering. So maybe let's call it MDO for brevity. And the definition is as follows. We take any subset A of the vertices of G, and we define the maximum degree ordering of A will be a sequence V1 up to VA, defined as follows. So first of all, V1 is the maximum degree vertex in the subgraph of G induced by A. So we take the maximum degree vertex, we delete it, and we repeat. So V2 will be the maximum degree vertex in the graph induced by A minus V1. V3 will be the maximum degree vertex in G induced by A minus V1 and V2, and so on. So here Vi plus 1 is the max degree vertex in G induced by A after we delete V1 up to Vi. And note that here I write the maximum degree vertex, even though it's not necessarily unique, but we can make some canonical choice of it. Suppose that we can enumerate all vertices of G by numbers from 1 through n, and say if there are some ties here in degrees, then we pick the one with the smallest label, so that this ordering is indeed unique. Now, so what was the idea of Kleitman and Winston? Well, the idea was to consider, while describing an independent set, is to consider the vertices of G with respect to this maximum degree ordering. And why is it a natural idea? Because an independent set, it's a very sparse set, so it somehow doesn't contain any vertices of high degree, and therefore if we display these vertices in this order, so this is the max degree vertex, then we have another one, and another one, and then when we were trying to see which of these vertices belong to the independent set, if we show this is the first one, then it already means that none of its neighbors can also be an I, because I doesn't contain any edges. And therefore, if we say, okay, this is the first vertex, then we can already delete these ones from consideration, and then we repeat. And by selecting a small number of vertices, we can reduce the remaining choices into a very, very small set, which gives us a good bound. So let's make it precise. So this is the algorithm. We start with the set A equals everything, and we do the following. So we repeat the following for S ranging from 1 up to Q. And so 1 will be, let V1S up to VAS be the maximum degree ordering on the set A. Now, number 2, we look at the vertices in this ordering. Maybe let me draw a picture here. So these are our vertices in this maximum degree ordering from V1 in the first step until Vn. Then as input, we are given some independent set I. So input is some I in I of G. Now, I ask myself, what is the first vertex in this ordering which belongs to I? And suppose it's VJS. JS is the minimum J such that Vj upper index S belongs to the set I. So what does this information, what does knowing this tell me? So first of all, I know that none of the previous vertices belong to I because VJS was the first. But also, I know that VJS is the maximum degree vertex in the graph induced by the rest. And since the set that we're enumerating is independent, then none of the neighbors of JS will ever belong to I. So the set A, which is the set of candidates for elements of I, we can delete from it everything up to JS and all the neighbors of JS to the right. So we delete from A vertices VS1 up to VS JS, but also the neighborhood of VJS. And so after repeating this procedure Q times, we return two things. The sequence of choices that we made, which is J1 up to JQ. And after repeating this Q times, the set A for candidates still possibly contains some vertices. And from these vertices, we know that all of the elements of I which didn't appear as one of the VJI, they have to be contained in this final set A. So we just return I intersection with the final set A, which is a subset of this final set A. So let's try to estimate the number of possible outputs, which will give us also a bound on. So first let's try to convince ourselves that this procedure is reversible. So instead of the set I will give you the sequence J1 up to JQ, and I won't tell you this set A J1 to JQ, but suppose that this set has some R elements, then this I is a subset of, this set is a subset of the set of R elements, so there's at most 2 to the R possibilities here. So I just tell you this sequence, and then the number among 2 to the R subsets, the number of the ones of this particular set. Now, can I recover I? So what would I do? I would do the exact same ordering. So I will repeat this algorithm, but here to define JS, I don't have to know what I is, because I already wrote down JS in my output. So I can repeat all the steps of this algorithm and recover, and the set A will behave the same way as it behaved when I inputted the set I. So in the end, I will be able to recompute this set, and therefore also recompute I. So claim the above encoding is reversible. Now, what about a bound on the number of outputs? So Q is just the number of ways I will repeat this procedure. So Q is just a free parameter. You can. So Q is just any. Q is any non-negative integer. You can choose Q for your. You can optimize Q depending on the context. But this is valid. For this to be valid, you need to input a set which is at use Q elements, so that you don't run into trouble here. So R will depend on the graph G, and it will also depend on Q. Okay, so this set A is a dynamic set in this procedure. So in the beginning, it starts as the whole vertex set. And then, depending on what I choose for J1, I can get a different set A in the second step. So A of J1 will be the one which I get after choosing J1. And here, this will be the final set after Q iterations when I chose J1 up to JQ. So what is the number of outputs here? Well, it's the number of sequences. Sorry, maybe let's write it like this. It's just the sum over all sequences J1 up to JQ twice 2 to the power A J1 JQ. This is definitely an upper bound on the number of outputs because the final portion needs to be a subset of A. And now, where this is a good bound, well, I can always bound it from above by the number of the sequences J1 up to JQ times twice the maximum possible cardinality over all sequences of AJ1 JQ. Now, J1 and JQ are just numbers, and we can bound their sum as follows. Each time when we select J1, we remove J1 elements from A. When we select J2, we remove J2 elements from A, and so on. And A in the beginning was a set of n elements, so this is at most n. So we have a sequence of Q numbers whose sum is at most n. Each of them is at least 1. So the number of such sequences is at most n choose Q times 2 to this maximum. I mean, all of them are at least 1, so it is n choose Q, not n plus Q choose Q. So now, so this is the procedure, And in order to derive anything interesting from it, we need to bound this quantity, which still looks somewhat mysterious. And note that here I haven't really used the fact that this is a maximum degree ordering nowhere. I just took any ordering, and I can still perform this, and I can still get the same bound. So the fact that for certain graphs this maximum is small is a consequence of the fact that I chose this particular ordering of the vertices. So in order to derive some bound on that, let's see what the algorithm does in one single iteration. So in one single iteration, we pick this vertex JS. Let's call this set A prime. We know that we will also remove the neighborhood of JS here. So we will remove, so the number of removed vertices is equal to the degree of VJS in the graph G induced on the set A prime. And here we use the fact that this is this maximum degree ordering. So this vertex VJS is precisely the maximum degree vertex in this graph. So this is just the maximum degree of G of induced by A prime. Now, this is maybe not such a nice quantity to analyze, so let's give a lower bound on this. Well, certainly the maximum degree is bounded from below by the average degree of this graph. So this is at least twice the number of edges in A prime divided by the size of A prime. Now, hence if the number of edges in A prime is at least, say, beta times A prime choose 2, if this graph induced on A prime has density at least beta, then the number of removed vertices is at least beta times A prime minus 1. But we will also remove JS itself. So in fact, I can add another one. So this is because we remove JS as well. And this is at least beta times A prime. And now let's try to conclude something from it. So let's analyze this procedure, and let's suppose that in the last iteration we still have a graph with density at least beta. Since this was a maximum degree ordering, it means that in all the previous iterations, every time I looked at such a set, it had density at least beta. So each time I lost a beta proportion of the vertices. If I iterated q times, then I will lose a proportion of 1 minus beta raised to the power q. And therefore, I will make progress as long as the density of what remains to be seen is still non-negligible. So let me now formulate the lemma, the conclusion of this discussion. So this is essentially due to Kleitman and Winston. So G is a graph on n vertices. we have an integer q and a real number r and a beta between 0 and 1. And we suppose that r is at least 1 minus beta to the q times n. And that for every a, which is a subset of the vertices, if A has at least r elements, then the number of edges that G induces on A is at least beta times A choose 2. Then for every M of size at least Q, which is at least Q, the number of independent sets of the graph G, which have precisely M elements, is at most N choose Q times R choose M minus Q. So in particular, the number of all independent sets is at most the ones which are smaller than Q plus N choose Q times 2 to the R. The number of sets which have exactly so independent sets with precisely M elements. Yeah, thanks. So let me convince you that this is indeed true. So it's enough. Yes. So let me prove this statement, at least hand wave a little. So it's enough to prove this bound. It's enough to analyze, to count the number of, to bound the number of outputs of this procedure, which is run on all sets of size M, which is at least Q. So we run this procedure, and we have all the possible sequences J1 to JQ. But then in the end, since I'm interested only in sets which have M elements, from the set AJ1, JQ, I only need to select the remaining M minus Q. Right, so this is the number of sequences times this maximum size, choose M minus Q. Now the number of sequences is still at most N choose Q. So I just replace this with 2 to this maximum by this maximum choose M minus Q. And the only thing I need to convince you of is that regardless of what I choose for J1 up to JQ, this number will be at most R. And then the statement will be proved. So claim is that this maximum is at most R. So proof, suppose it's not. If it's not, then there exists a sequence of J1, JQ, where this AJ1, JQ is strictly greater than R. So suppose not. then there exists a sequence J1, JQ with a J1, JQ is strictly greater than R. Now, when we were at this step, it means that this set had at least R elements, right? Because the final set we will obtain by selecting this last vertex and maybe deleting something. So in every step, this set had at least R vertices. Now, let's look at our assumption. Every subset of size at least R has density at least beta. And in particular, this vertex had degree B times alpha prime minus 1. Together with him, it's B times A prime. Beta, yeah, change. Beta times A prime. But also we have these vertices in the beginning, and this is the difference between A and A prime. So the number of vertices we removed was A minus A prime plus beta times A prime. And since beta is at most 1, this is at least beta times A, which means that in each of the Q steps, the set A shrank by a factor of at most 1 minus beta. But if we, so 1 minus beta times Q, after Q steps it shrank by this factor, we started with n vertices, we would have at most R left, which is a contradiction.
So maybe the but they don't
below beta, but is yes, that's true. Okay, so this is the proof. I mean, maybe I didn't do it in the most formal way, for which I apologize, but I hope that at least the main ideas are clear. So now, in the remaining half hour, I'd like to show you what I think is an interesting application of this result, of this idea, to the problem of counting sum free sets among integers 1 through n. So the result I'm going to prove to you was originally proved by Noga Alon in 1990 with similar methods. But what we get from this statement is a slightly sharper estimate. So illustration. Sum free sets in the set 1 up to n, and this was a problem posed by Cameron and Erdős. So what did Cameron and Erdős ask about? Maybe first let me tell you what the sum free set is. So a set A in integers 1 up to n is called sum free if and only if I cannot find 3 elements x, y, z in A, not necessarily distinct, such that x plus y is equal to z. Now, one might ask themselves the question, how large can such A be? There's a fairly easy lower bound. So what would be your guess? How many elements can I take from 1 to n if I want to avoid having sums? Yeah, so I can either take the top half, or take the odd numbers. So there are 2 candidates. So it's at least the maximum of what is the number of odd numbers? It's n over 2. And then I take the ceiling because we start with an odd number. But I can also take the top half, which is n divided by 2, but now I'd need to take the floor.
That's very easy.
Sure, yeah. So this is n choose 2, but sorry, I wrote it in this way because I want to say something more. Now, okay, so let's keep it like this for a second, but let's remember that these are the odd numbers, and this is the top half, because we'll use it later. Now, so I'll convince you that actually, I mean, I'll prove to you that n over 2 is the maximum we can take, and why is it so? Suppose that.
But if you take top half, you know, and a little bit more, you're still on the safe side.
No, if I take anything which is at most n over 2, then n over 2 plus n over 2 is equal to n.
In XYZ, repetitions are allowed. You can take x and 2x.
No, but that's, if n is even, like 2, you take n over 2. If n is odd, like 1, you take ceiling of.
Oh yes, 2 3. Yeah, you're right. So it's it's also the ceiling. Okay. That's even easier, yeah. But let's keep it like this. So now I'm going to also prove to you that A is at most the ceiling of n over 2, if A is sum free. For this, let little a be the largest element, and look at the set A minus A. So I subtract from A each element of A. So I get A elements. And this is contained in the set 0 to n minus 1. But the crucial part is that this is disjoint from the set A itself. Because if A minus A and A had a common element, then I would have some B and C such that A minus B is equal to C. So A plus C, B plus C is equal to A. Disjoint from A and the same number of elements as A. So now I have two disjoint sets of equal size contained in the number 0 to n, or actually 0 to A. Hence, A plus A minus A is at most A plus 1, which is at most n plus 1. But A minus A has the same cardinality as A. So I get this inequality. So A is at most n plus 1 over 2 floor function, which is the same as ceiling of n over 2.
Did you use much less? Did you really use some freedom, or just the inexpressibility of the biggest element?
Limit is a sum.
This is a useful thing to know. Floor of n plus 1 over 2 is ceiling.
Yeah, but as you could see earlier, I'm not an expert on floors and ceilings, so maybe.
You can talk to your neighbors from one floor and they knock on the
So this solves the extremal question here. What is the maximum size of a sum-free set? But what Cameron and Erdős asked was, how many such sets do we have? How many such A are there? Now, of course, every subset of the maximum sum-free set is sum-free. So this gives us at least 2 to the ceiling of n over 2. But here we have actually two sets of the same size, which have very, very small intersection. So, I mean, most of their subsets will be completely different. So actually we have twice. So this is at least 2 minus little of 1 times 2 to the n choose 2. So this, I mean, this problem is somewhat more complicated than, say, counting all the triangle-free graphs, where we know that a typical triangle-free graph is bipartite, because here we have these competing extremal structures.
Are you asking for the number of sum free sets or maximum sum?
Number of sum free sets, not maximal. That's, yeah, thanks. That's a good question.
Could you repeat the bound?
The bound, so every subset of one of the maximum size sum free set is sum free, but they intersect in only n over 4 elements. So only a small proportion of this. So
The double counting is
yeah.
now 2 to the quarter.
Mm-hmm.
And there are no other maximal sum free sets, right?
There are others, yes.
There are others maximal.
Yes, yes. Because if we, if you somehow include just a few elements, so slightly smaller than n over 2, then you will have to remove a few elements which are close to n, and you will get a set which has almost n over 2 elements. So actually, the number of them is quite larger.
No, I mean, but the maximal, like apart from these two, like.
Yes, the maximum size. No, these are the only two maximum size. Mm-hmm. Because yeah, I thought so maximal are the ones that you cannot add it. Mm-hmm. Now, a question of Cameron and Erdős, actually a conjecture. And I think this is 1990, was that the number of sum free sets in 1 up to n is still at most a constant times 2 to n over 2.
So wait, okay, that's no worries.
Mm-hmm. Now this conjecture was proved, so this is now a theorem proved by Ben Green and Saposhenko. This is around maybe 2004. Actually, they proved that there exist two constants, C0 and C1, such that the number of sum free sets in 1n is asymptotic to C, where we have two constants depending on the parity of n, plus little of 1 times 2 to the n over 2.
These constants are not given by this example.
No. So this I don't know what these constants are.
So you have, this means that you have further.
You have, so if you say, if the smallest element in your set is, say, n over 2 minus 7, then the largest is maybe n minus 14, and every subset of this is sum free. And this is I mean practically n over 2 elements. And most sets will contain something which is smaller than n over 2. So this, I think you get this constant by summing some infinite series. And what so our illustration.
Conjecture was proved before that, right? I mean, it's just the final. I mean, the conjecture and the formula statement, was it proved before, like some constant, or?
No. This is they were the first to prove this conjecture, and moreover, they proved this sharper estimate. But what Noga did, so almost 15 years earlier, Noga alone, so this is I think 91, proved that the number of sum free sets in 1 up to n is equal to 2 to n over 2 plus little o of n. So he proved a weaker form of this conjecture, giving the asymptotics for the logarithm of this number. And this will be our illustration. And Noga's proof uses very similar ideas to what I told you just now. So let's I'm going to use a somewhat different argument in the same spirit, and we're going to input our lemma as a black box at a certain stage of the proof.
Can you state again the lemma?
Oh, sure. This is actually, yeah. Actually, I'm not sure if I'll have the time to use the lemma today. So maybe let's keep it here until the end, and I'll work on the other boards. As G has n vertices, we have an integer q, an r, and a beta, such that n times 1 minus beta to the q is at most r, and for every subset A of vertices, if A has at least r elements, then the number of edges that A induces in G is at least beta times A choose 2. Then for every M at least Q, the number of independent sets of size M is at most N choose Q R M minus Q. Okay, so let's start with a very, very easy observation. We will separately count the number of sets, number of sum free sets, which have no small element.
We might as well ignore the parameter r and write everywhere n times 1.
Yes.
There's no gain in
There's no gain in this, yes. But usually in application, somehow you know what R is convenient for applications. So the number of... no, sorry, you cannot replace it with... Because maybe if you then increase Q by a factor of 2, then this number will go down dramatically, but it will no longer be true that if you take a set A of size at least n times 1 minus beta over Q, that it will be dense. So R, somehow the way you apply it, first you find R by reverse engineering this condition. So this has to be the smallest number so that every set of size R still induces a non-negligible portion of edges, and then you choose Q so that this is satisfied. So the number of sum free sets with fewer than n to the 2/3 elements smaller than smaller or equal than this ceiling of n over 2 minus 1. So this is easy to count, right? Because we have at most n to 2/3 elements here, and the remaining ones, well, any subset. This is 2 to the n over 2 plus 1. And this is 2 to the n over 2 plus some constant times n to 2/3 times log n. N to 2/3 elements which are smaller than n over 2 minus 1. Yes, sorry.
How do you present it in the lower part?
So this is just for convenience, and this shows that the difficulty lies in counting the sets which contain many elements which are smaller than n over 2. So for other sets, for other A, let S of A be the set of n to 2/3 smallest elements of A. So by assumption, we know that all these elements are in particular smaller than at most n over 2 minus 1. Now, so now we relate this problem to the problem of counting independent sets in a particular graph. And we do it in the following way. So given some set S, which contains only elements in our range, we define the graph GS with the vertex set 1 over 1 up to n, and the edges are the pairs x, xy, such that y is equal to x plus or minus s for some s in S, but actually I want to do it modulo n. So in other words, I look at the numbers 1 up to n on a circle, and then for every element of S, I will just draw a number of chords. Now, note that G is 2S regular, because if I fix any x, then if I add any element of S, I have S of them, or subtract any element of S, then this will define an edge. And since S contains only elements smaller than n over 2, then no S is equal to minus S modulo n. But the crucial thing is this following observation, is that if A is sum free, then A minus SA is an independent set in the graph G SA. So let's prove it. Suppose not. Then we have two elements, not necessarily distinct, x and y in A, but they're not among the smallest element of A, so that x plus s is congruent to y modulo n for some s in S of A. S of A is contained in A, so to reach a contradiction, I only need to prove that this holds also not necessarily modulo n, but as real identity. And this is true because, so here somewhere I have S, and this is where the smallest elements end, and x and y are somewhere here. And since S is smaller than x, then there's no way I could wrap it around. So really, x plus s need to be equal to y. So since s is smaller than x and y, then x plus s is really equal to y, which is a contradiction. Okay. Now, why is it good? Because we have the following corollary of lemma, which was originally proved by Noga in the same paper, and then versions of it were reproved by Sapozhenko. So the version due to Sapojenko is the version whose proof I'm going to present now. And also stronger statements have been proved by Jeff Kahn and Yufei Zhao. And the statement is the following. There exists a constant C such that for every deregular graph G on n vertices, the number of independent sets in G is at most twice 1/2 plus a constant square root log D over D times n. So if any deregular graph cannot have an independent set which is larger than n over 2, you can convince yourself that this is true by just double counting edges. Right? If the set was larger, then it would send too much mass, which has to be received by the other half. But actually, it turns out that not only it doesn't have large independent sets, actually the number of independent sets is not much bigger than the number of subsets of the largest one. So I think I'll have to postpone the proof until Wednesday, but let's at least derive the statement we're interested in from this statement. Well, now it's becoming trivial because the number of sum-free sets in 1 to n, well, we have this first case where they have few elements smaller than n over 2, and this gave us f 2 to n over 2 plus n to 2/3 log n. Plus, we have this other term, which we get from here. So here we choose the number of sets S, the number of different sets SA, which are sets of n to 2/3 elements from 1 up to n over 2. So this is at most n over 2 to n to 2/3. Now, once we fix such a set SA, then since the remainder of the A minus SA is an independent set in this graph, which is already defined by SA, then I can upper bound it, the remaining choices, by the number of independent sets in this graph GS. But this graph GS is 2S regular, and S is n to 2/3. So I just plug in n to 2/3 for D here. And what I get is 2 to n over 2 plus a constant times square root of log n to 1/3 times n, which is everything together is 2 to the n over 2 plus a constant n to 2/3 times log n. So actually, we got a slightly stronger statement. I only claimed a little O of n here, and we proved an estimate of the form C constant times n to 2/3 times log n. Okay, I think I'll stop here, but I still can take some questions.